Newton-Raphson for logistic regression, like few administrative things. Like first of all, I have to swap the theory and lab once again next week for unavoidable reasons. Okay, hopefully this won't happen again, but I have no other options. Like so next week, yeah.
Question regarding the midterms. Is there a place in the drive where we can find the solutions for a set midterms?
No, I'll come to that. Wait. So what the first announcement is we are going to have the lab and theory swap next week as well. So Wednesday is going to be office hours for assignment 2. Okay, and Thursday is the class. Same as this week. Okay. Then about the midterms, like so, how many of you have started looking at the sample questions that I have put in the drive? So just a few people. Okay, so there are no solutions for that. Like so, well, that's an exercise for you. So I will let you like come up with the solutions. Of course, you are free to discuss your solutions with your friends through Piazza. And if you have any questions, you can post it in Piazza and TAs would answer. But please don't post the question and say, okay, what is the answer for this? Right? Like, so if you're stuck at some point, post your solution and somebody like a TA or a student will help you. Okay. But in general, like I recommend that you practice all the questions that were out there the last 2 years. And so one of the students commented during the break that last year's midterm was much harder than the year before. Maybe the trend will continue. So prepare well in advance. Okay. So and I couldn't upload the recording of the last week because I just came back yesterday. I uploaded the first part out of the 3 parts, but I'm going to upload every part, like all the parts for last week today. And as soon as I get the recording for today's class, which is usually tomorrow, so then I will upload it. Okay. So I highly recommend you to go back and watch the recordings once again, like for topics that you're not comfortable with. Okay. Okay. So now let's continue. So before the break, we looked at how to do Newton-Raphson for linear regression, where we discovered that if your objective is quadratic, you reach the solution in 1 step. And that is not surprising because Newton-Raphson is actually making this quadratic assumption and it jumps to the solution in 1 step, right? Okay, so now we're going to do Newton-Raphson for logistic regression. Okay, so in the case of logistic regression, the error function is given by minus ln p of t given w, right? Which is basically summation n is equal to 1 to capital N, Tn ln yn plus 1 minus Tn ln, 1 minus yn. Okay. Okay, so the gradient here is going to be we already derived this gradient, right? So we don't need to do it again. So it's directly, I'm going to write it directly. So it's summation n is equal to 1 to capital N yn minus Tn times xn, right? So which is, well, I can write this as x transpose y minus t if I want to write this in vector notation. Okay. Now the Hessian is given by summation n is equal to 1 to capital N. Okay. Just give me a second. Okay. So let's do that actually from this term. Yeah, I'm differentiating this term once again with respect to W. Okay, so this is going to be 0. So when you differentiate, this is going to be the position of this times xn, right? So it's going to be yn 1 minus yn when you differentiate yn times when you differentiate internally, you're going to get x. There's already one x outside, so this is what it's going to look like. Okay. So when I differentiate this equation with respect to w, this is what I get. Okay. So I can write this as x transpose r x, where R is a diagonal matrix. Okay, R is a n cross n diagonal matrix with R and n being yn times 1 minus 1. Okay, so now I can use these two equations to write the Newton-Raphson update rule. So W new is equal to W old minus x transpose R x inverse times x transpose y minus t. Yeah. Okay. So I can take x transpose R x inverse as common. Then this becomes x transpose R x inverse times W old. Okay, sorry, there's no here. Okay, minus x transpose y minus t. Okay, so this can be written as W new is equal to x transpose R x inverse times x transpose R z, where z is a n-dimensional vector represented by x W old minus R inverse of y minus t. Okay, so I'm just writing it with z and r so that the equation looks something like this. Okay, so this looks like the solution of d square, which is x transpose x inverse x transpose y, right? However, we have an r here, which is actually a function of y again, right? So which means you're not going to get the solution in one step. You're going to repeat this again and again. So you're repeating this b squared solution again and again, right? And so Newton-Raphson for logistic regression actually has a name. So this is called iterative reweighted least squares. Okay, where the reweighting is happening through R. Is it here? The name doesn't matter, right? As long as you know how to compute the Newton-Raphson update rule. So that's all that matters. Is it clear? Okay, so before we conclude, like I want to talk about one of the issues of doing maximum likelihood, okay, with linearly separable problems. Okay, let's say you have a linearly separable problem. Like, what do I mean by that? So I have some circles and crosses, and I can separate them using a line. Okay. Now, what would happen when you do logistic regression with linearly separable problem is you will quickly find the decision boundary, right? Like, so all you have to do, you start from any random line, you do gradient descent, you're going to find this decision boundary, right? However, you're not, the error, the error is not going to be zero in the sense it's going to approach zero, but not zero. Why? Because we're doing sigma of W transpose x is equal to 0.5, right? Like, so once you reach that point, then I can just keep increasing the value of W forever. And that sigma is going to be 0.5. So which is basically like you find the direction and then you're just stretching the line in the direction, right? Like, so which you could continue doing forever. So what would happen when you normally run logistic regression with linearly separable problem is you'll find the decision boundary which has zero training error. Then the algorithm will not stop, like it will just, because the sigma will never exactly become one, right? If you're just going to approach probability one, like or zero, right? So you will just keep increasing the value of W. And at some point, you will run out of the numerical precision in your computer, and like so the program will crash. Okay. If you want to try this, you can actually try this. Like so, like try running logistic regression with a linearly separable problem. You will see that the W keeps growing at some point. The algorithm, like the program breaks. So how can you fix this issue?
Into confidence.
Sorry.
Confidence intervals.
Oh, what does confidence interval mean here? So the problem is when you do gradient descent, once you find the solution, W keeps increasing and then it is crashing. So how can you fix this?
Stop the number of iteration.
When?
Yeah.
Well, that's one heuristic. Like, so you could, whenever you get zero training error, you could stop. Okay, but it's not very ideal because you could also get zero training error somewhere here and you're immediately stopping. Yeah.
Is there like adding a constraint like we did in week 2 when the W grew too much?
Yeah. So what kind of constraint is that? So basically some sort of regularization, right? Like so whenever you know that your problem is linearly separable, you should always add L2 regularization.
So can you repeat again why the W is growing? Like I still can't see why.
Because like what matters for the decision boundary is the direction, right? Like not the W, like not the magnitude. So there are infinitely many solutions so that would have the same direction, right? So what would happen is like when you're doing gradient descent, like you will keep updating W as you maximize the likelihood. So you're just going to keep adding some small value to W again and again and again. It's going to blow up.
Okay.
Is it clear? Any question? Okay, so that concludes our discussion on logistic regression. Okay, so now we are going to see another family of models. Okay, so we are actually covering all the three families of classification models today. So we started the class today with generative models, right? So the idea of generative models is to model P of X comma Y and then use that with Bayes rule to compute the class probabilities, right? So examples for generative models include GDA, Gaussian naive Bayes, Bernoulli naive Bayes, etc. Right? So then we looked at discriminative models, where the idea is to simply model P of Y given X, right? So the algorithm that we have seen is logistic regression, right? So have you seen any other discriminative models in this course so far? Have you seen any other discriminative models?
What do you mean by discriminative model? Like,
Models, well, like something that models P of Y given X. Any other? Yeah?
CNN.
KNN, right? Like, so if you think about how KNN works, you compute the probability of the class given the neighbors, right? So it's actually P of Y given X, you find the neighbors and use that to compute the Y. So it is actually P of Y given X, right? So K nearest neighbor is another example for discriminative models. Okay. So now, even though they both differ in terms of complexities, like so they are both probabilistic models. right? So, so why should we just use probabilistic models for classification? So we could also do classification models which takes the input and tells me what the class, right? Like I don't need probabilities, right? So that is the third family of algorithms. Okay, so this spectrum is in some sense like dependent on like how probabilistic these models are. So in the right end, like we have what people normally call as discriminant based models. Okay, so these models, they just directly model y as some function of x, and this f need not be a probability function. It's just some score. So it's going to tell you, oh, score for class 1 is this, score for class 2 is this, score for class 3 is this. If you want to put a probability on the top of it, you could, like, but if you just want to use the scores directly, you can do that as well. Okay, so have we seen any discriminant based method for classification? Hmm? Yeah. Yeah. So have you seen any methods that instead of giving us the probability, just give some f of x?
Linear regression.
Linear regression, right? If you do linear regression for classification, which is what we did as soon as we started with classification, right? If you remember, when we started with classification, we said, okay, why don't we just try linear model or a K-nearest as neighbor, right? Like, so when you do linear model, the model is just giving you some number, right? In a -1 classification, we took the number and said, oh, the number is positive, I'm going to call this class 1. The number is negative, I'm going to call this class -1. Right? So linear regression is an example of an algorithm that is discriminant based. But we also discussed it's a really bad algorithm for classification, right? Like so, like it's not using any of properties of the classification problem. So we need better algorithms. Okay. So for today's class and also for the next class, like we are going to look at family of discriminant based methods. Okay. And this family of methods is called separating hyperplane methods. Okay, as the name suggests, these algorithms will try to find in 2D a line, a 3D a plane, in high dimensions a hyperplane. Okay, it's trying to find a hyperplane that separates class 1 from class 2. Okay, so we are directly trying to find the plane. Like, so we are not doing probability distributions here. Is it clear? Okay, so how would it work? Like, so for example, let's say I have a problem which looks like this. Okay, there are two features for x1 and x2. So we're going to search for every possible plane that separates these classes in 2D is a line, right? So for example, so this is an example hyperplane. It's not a good hyperplane, right? So then you can try this. No, you could try this. You could try this. So the last hyperplane that I drew actually separates, right? So that is a good hyperplane when compared to the rest of the hyperplanes. Is that clear? So now we will talk about how to find this hyperplane. Okay, and different algorithms are going to be differing on the procedure. So before we do that, so here is a quick comparison with least squares, right? So for this particular problem, if I do GDA or least square, they are going to have, okay, you don't see the lines, there are two lines here, they are on the top of each other because they're very close together. So you're going to have the solution for least square and GDA here. And here are two hyperplanes with zero error. Okay, so our goal is to find the hyperplane which has like as minimum error as possible. Is it clear? Okay, how are we going to do that? So we will start with one of the simplest discriminant-based methods, okay? Some machine learning classes actually start with this algorithm, okay? Perceptron, simply because this was probably one of the first machine learning algorithms people invented. Okay, so perceptron was invented by Rosenblatt in 1958. Okay, when we did not even have proper computers yet. Okay, so this was the first learning algorithm that was invented, and this is how perceptron works. Okay, it's a really simple algorithm. So y of x is given by f of w transpose x. Okay, it's a linear model. So simple linear model with some function on the top, right? So this function, I'm going to define this function as plus 1 if a is greater than or equal to 0, and minus 1 if a is less than 0. Is it clear? So it's a binary function, right? So this function takes w transpose x. If w transpose x is greater than 0, it is plus 1. If it is less than 0, it is minus 1. Is that clear? Any question? Okay. Now, how do I learn the w? Right? So how do I learn the w? So what Rosenblatt did is to actually directly work with the misclassification error. Okay. So the misclassification here is simply the 0 loss. Okay. So we're going to try to minimize the 0-1 loss with the perceptron algorithm. Okay, so which means my loss is 0 when the answer is correct. It's 1 when the answer is wrong. And I want to minimize the sum of the 0-1 loss. Is that clear? So this loss is not a good loss for gradient descent, by the way. Okay, so we cannot do gradient descent with this loss. Why? Look at this. Let's say I have data point like this, and let's say my current, sorry, start with this. Okay, this is my current decision boundary. Okay, now what would be the 0-1 loss for this decision boundary? There are 6 examples. How many of them are misclassified? 1. So the sum of the misclassification. So what is the misclassification error here? 1, right? So for this example, the misclassification error is 1, right? Now let's try to move this little bit by using gradient descent. Okay, like imagining that you can get some gradient information somehow, right? Like so, like if you try to moving this little bit. Okay, so let me see if I can draw this. So like you can keep moving this line. Now, if you compute the misclassification error for all these lines, it's going to be same, right? Which means you're going to get 0 gradient. So the gradient is 0 for all these lines. And when you eventually cross this example, you're making some progress. So you're going to get non-zero gradient. Okay, so which means to go from here to here is not an easy thing to do with gradient descent on the total misclassification error. Is that clear? So what we are going to do is, well, what Rosenblatt did was like something smarter, like so, like he basically computed the misclassification error, but then tried to minimize the gradient only for the mistakes. Okay, because when you make a mistake, you're going to get gradient. So let's see how that happens. So the error function that we use for perceptron is called perceptron. Sorry, perceptron error criteria. Okay, this is what we're going to do. Like, first, let's start with some assumption that if observation that if xn is in class C1, then W transpose xn is greater than 0. Right? For class 1, if it is in class 1, the value is positive. Okay. Similarly, if xn is in class C2, which is -2, let's say, then W transpose xn is less than 0. Okay, my T is +1 or -1. Okay. So then for any xn, can I say that W transpose xn times Tn is always greater than 0? This is true, right? So when Tn is +1, so positive minus multiplied with positive, this is greater than 0. When Tn is -1, this is negative, right? So minus times minus again positive, right? So either Tn is +1 or Tn is -1. For both terms, W transpose xn times Tn is greater than 0, right? So I just need to maximize W transpose xn Tn. I want to make this positive for all the examples, yes?
Tell me the positive the impedance specified.
Yes. So this is positive when the classification is correct, right? So the goal here is to maximize this for all the examples. If I maximize this for all the examples, then it is going to become greater than 0 for all the examples. So which means I have found the plane surface, right? So maximizing this for all the examples is actually equal to minimizing this for minimizing minus W transpose xn. They are both same, right? Now the error criteria, let's write this as EP of W, is basically minus summation over n belonging to some set mu W transpose xn Tn, where mu is a set of all misclassified examples. Okay. As you can see, this error function is actually piecewise linear. Okay, so if I just compute the gradient for one example, right, then this is going to become W nu is equal to WO minus eta times the gradient of the error function. So it's going to be WO, okay, minus eta times. When you differentiate minus W transpose xn Tn, you're going to get minus xn Tn. So this becomes plus xn Tn, right? And we are just finding the plane. So only the direction matters. So the magnitude doesn't matter. So I'm going to set eta is equal to 1. This becomes WO plus xn Tn. Is that clear? Now, this is how the perceptron algorithm is going to look like. Okay, so I'm going to initialize the W random V. Okay, so then I'm going to repeat until all the data points are correctly classified. For each data point, I'm going to check if the prediction is actually equal to the target. So then I don't do anything. Okay, if the prediction is correct, I don't do anything. Otherwise, I'm going to take a step in the direction so that the prediction becomes correct. Is that clear? It's a very, very simple algorithm to implement, right? And you can prove theoretically if you want that this algorithm will converge if you have linearly separable problem. It has to converge, okay? And that is called the perceptron convergence theorem. Okay, which says that if the problem is linearly separable, perceptron algorithm will converge. I'm not going to do the mathematical proof, but I can do an intuitive geometrical proof. So let's say I have a problem like this. Okay, and I start somewhere here. Okay, so you see that it makes mistake for these two things, right? So which means you're going to push the vector, the line to the left when you do the gradient, right? So you'll push it like this and it will reach somewhere and then you will stop. So the argument here is you're just moving the line. You keep moving the line, right? As long as you're moving it in the right direction, you have to stop somewhere, like where the error is 0. Okay, so this is true even if you start here. Even if you start here, there are 2 errors. So you will move here and then you will stop. Is that clear? Yeah. Okay, many questions.
Just to make sure this algorithm only works if it's separable.
Yes, we're going to talk about this. So this is going to converge only when the problem is linearly separable. What would happen when the problem is not linearly separable? When, okay, let's say I actually add a circle here and cross here. Okay. So this algorithm will never converge. Because why? Because it's going to come here. It's going to come here. There's one error, so it will move this line. There's another error, so it will move this line, right? It's going to keep oscillating between the two, and it is not going to converge. It's a good observation. So, and there were a few other hand raises. So, yeah.
Why will we take the disqualify the contribution of the error?
Sorry, can you please repeat the question?
Why do we only take the
Oh, yeah. So that's because the error is 0 when things are correct. We are doing 0, 1 loss, right? So when the prediction is correct, the error is 0. So you don't need to worry.
Okay.
Any other question? So here is an example of how perceptron would work, right? So you see, you're starting here. So there is one misclassification. Okay, so which means you're going to move the direction a little bit, right? And then you look at the next example that is also a misclassification. You're going to move a little bit. And when you reach here, you're going to place it right here. The two. Is that clear? Any questions so far? Okay, so let's talk about the issues. So this algorithm actually has many issues. So, well, as you can imagine, this was the very first algorithm, right? Like so the first issue is if the data is not linearly separable, then there is no convergence. In fact, it's going to keep oscillating and never converge. Is that clear? Now you will never know this unless you know you have a way to detect cycles. You will just run the algorithm. It's going to keep continuing. Like it's going to make some progress, reduce, like then go back. Some progress, like worsen, some progress worsen, right? Like, so you will never know whether there's a cycle, right? It's hard to detect cycles. Second issue is, well, maybe let's go here, right? I wish I drew it separately, but okay, I'll draw again. So let's say I have a bunch of examples like this. Now, the second issue with this perceptron algorithm is if I start from here, I would probably stop here, right? Similarly, if I started from here, I would probably stop here, right? So these are both, oh, sorry. So these are both valid separating hyperplanes. They both have 0 training error, but which is the best among these things? We don't know. Okay. Maybe, well, they are both not best, okay? So we will talk about it in the next class. But for now, the issue is every time you run perceptron algorithm, it's going to give you different solutions. And it is not clear which is the best solution. Okay, so which is the best solution? We will talk about it. Okay, so for now, the issue is solution in linearly separable case is not unique. Okay. The next issue, again in linearly separable case, is when the gap is too small, this algorithm is going to struggle. Okay, so for example, I have data points like this. Okay, so the gap is so small that, oh, sorry. Okay, no, no. Okay, something that separates, right? So the gap is so small that finding this is going to be a big problem. So the algorithm is going to keep moving between like one misclassification here and there. Okay, so the issue is the convergence is very slow when the gap is small. Is that clear? Any questions so far? Okay, so I think we will stop here. But for the next class, we are going to continue our discussion on perceptron. So I highly recommend you to rewatch perceptron or learn perceptron before you use it. But I will start from perceptron and see how to make it work for non-linear separable powers. How to make sure that perceptron has unique. Okay, so we will stop here. Thank you.